Okay, so now what we're going to do is we're going to introduce exponentiation. Basically reintroduce what powers are. And you may ask, well, why would we need to do that? We already know what that is. And that's sort of true, right? If you have a number raised to a power, well, we know what that means if that power is a rational number, a fraction, right? Because you take the bottom of the fraction and make that a root, and then you can have the root, the tth root of a to the s power. So this is all well and good, but the problem is it only makes sense if you can actually do that. And remember, the numbers that you can express as fractions of integers, those are called rationals. And so our goal is to have this make sense for all real numbers. P is a member of the set of all real numbers, not just rationals. So, how do we get there? Well, what we're going to do is we're actually going to use the natural logarithm. We have defined that rigorously. That makes sense for all real numbers. So what can we do? Well, let's take a look at the natural logarithm. Y equals the natural log of x. I drew that picture last time. If you were to graph it, it would look something like this. It's 0 at 1, and it goes down to negative infinity as you get closer and closer to 0. And it goes up to infinity rather slowly, but it does go up to infinity for larger values of x. Here's my x-axis, here's my y-axis. What's the point? Well, the point is that it's a differentiable function, and it's what we call a one-to-one function. It passes the horizontal line test. And what does that do for us? Well, that means it has an inverse. So what I'm doing basically is swapping my x and my y. And what would that look like? Well, instead of the one being on the horizontal axis, now it's on the vertical axis. And we're going to go up like so, and go down like that. And this is the graph. So let me maybe move this around a little bit. This is the graph on the left of y equals natural log x. This is the graph of x equals, and we're going to call this exp of y. And that's going to be the inverse function of the natural log. So it looks exactly the same, it's just been mirrored on its side. And we're going to eventually going to call this e to the y, but we'll have to give a good reason to say that in just a moment. So let me write this in words, so we have it in words. So basically what we're saying is if f of x is equal to the natural log of x, let the exponential function exp of x be f inverse of x. And the nice thing, one of the things we probably mentioned real quickly in Calculus 1 is that the inverse of a differentiable function is also differentiable. Okay, so since this is differentiable, and that makes sense because there's no corners on it, right? So that's differentiable. So is its inverse function, exp. So what can that do for us? Well, I want to prove that this function exp of x is its own derivative, because I'm going to eventually say that this is the same thing as e to the x. So here's an example problem. Okay. We're going to use this theorem from your Calculus 1 class. I'm going to remind you of it. This is not something I expect you to have memorized. I would remind you that the derivative of an inverse function is 1 divided by, the function has to be differentiable, so this is a prime right here, f prime of f inverse of x. I'm going to use that fact to prove that the derivative of the exponential function, exp, of x, which I'll eventually call e to the x, is just itself. All right. So how do we do that? Well, this is basically just using definitions here. I want to find the derivative of the inverse function. Exp of x is the inverse of the natural log. So I'll use my formula that I had up here. F prime of f inverse So what is f inverse? Well, that's exp of x. And what is f prime? Well, remember, what is my f in this case? In this case, my f of x is the natural log of x. I'm assuming that f of x is the natural log. That means f inverse is the exponential function. The natural exponential function, I might call it. And, all right, well then finally, what's the last thing I need to know? Well, what's f prime of x? Well, we're taking the derivative of natural logs. That's just going to be 1 over x. So putting that back over here, I've got 1 over, f prime is 1 over exp of x. And hey, if you're dividing it twice, you're just undoing yourself. 1 over exponential x is just exponential x. And that finishes the proof right there. Sometimes we draw a little black box to say we've finished a proof. But you don't have to do that, of course. All right, so that's good. We've now proven that the derivative of this thing that we will call e to the x, and just in the next section, it has its own derivative. So that's good news. What else can we do? Well, first of all, what the heck is e? You've probably been told what e is, but I'm going to define e for you officially, and e is simply going to be the value of the exponential function at the number 1. So I drew a picture of the exponential function for you. Here it is again, the quick sketch of it. So the value of the exponential function at 0 is just 1. The value of the exponential function at 1 is whatever this height is. Turns out it's about 2.718. So e is equal to about 2.718. Now, why is it about 2.718? Well, that's actually one of the things we're going to have to work up to. That's one of the goals of this semester, is being able to approximate numbers like e. And that'll take us most of the semester to get to, but I promise we'll get there. So, until that time.